Hi, I'm Shanaz. In last lecture we did cyclic modules. So let us recall what do we mean by cyclic modules. So suppose we are given a ring R. So suppose we have this ring R, and then an R module M. This is said to be cyclic if there exists some element x in M such that this M is actually R times x, i.e. it is generated by x. So in that case we say this M is an R module. So now let us do a small proposition. So we have this proposition. So it states that an R module M is cyclic if and only if M is isomorphic to some quotient group R mod I, where I is some ideal in R. So an R module M is cyclic if and only if M is isomorphic to say R mod I for some ideal I in R, for some ideal I in R. So this is actually a trivial exercise. So let us do the proof of this result. Now to prove if M is isomorphic to R mod I, now R mod I being cyclic generated by the unit element of R, so in that case M is of course cyclic. Now if M is cyclic, we have to prove they are isomorphic, so we have to exhibit a map, a homomorphism between M and this quotient module R mod I, which is actually bijective. So let us define. So define a map, say phi from R to M. Now this phi is given as, now phi takes an element in R and it takes this element A and it carries out this A to AX. Actually this is called the multiplication map. So here we multiply by X. Then one can note here phi is actually a module homomorphism. Now M is an R module, and R being a ring, it is module over itself. So this is actually a map between R modules. So it is a trivial exercise to prove this phi is homomorphism. So clearly phi is a homomorphism, actually an R module homomorphism, R module homomorphism. So one can see here, if I take two elements A and B in R, then phi of A plus B, this goes to A plus B of X. Now using R module properties of M, this is equal to AX plus BX, because the scalar multiplication of module M is compatible with the addition in the ring R. So this is actually phi of A plus phi of B. So here we note that phi is additive. Now to prove the homogeneity of phi, if we take phi of R times A, this is actually R A of X, then again this is R of AX, because the multiplication in ring R and the scalar multiplication in module M, they are compatible. Here this multiplication takes place in ring R and this is the scalar multiplication here. So these are not the same operations here. This is the operation, multiplication operation in R, and this is the multiplication operation in scalar multiplication of R with M. Now since these two operations are compatible, we have this expression here. So this is actually R of phi of A. So this is also homogeneous. So that is why this phi is a homomorphism. Now let us exhibit the kernel of phi. So phi is an R module homomorphism, since phi of A plus B is actually A plus B of X. This is same of phi of A plus phi of B for all A and B in R, and phi of R X, this is R of Rx of A, sorry, this is RA here, this is RA of X, this is actually R of AX, this is R of phi of A. This is for all R and A in R. So we have assumed here that M is cyclic. So M is generated by, so let us assume here, so let M is cyclic, i.e. M is generated by X. Then we define a map phi from this phi from R to M. Now since this M is actually a cyclic module, so this phi is definitely a surjective homomorphism. So also phi is surjective. The reason being M is generated by X, since M is generated by X. Now we have this surjective module homomorphism between R and M, so we can invoke the first isomorphism theorem of modules. So therefore, by first isomorphism theorem, we have this homomorphic image, which is M. This is actually isomorphic to quotient group of R, that is R mod, it is kernel. Now if we put kernel of phi, now kernel of phi indeed an idle in R. So take I is equal to kernel of phi. So we are through. Now converse is trivial because R mod I being cyclic, since R mod I is generated by one bar, therefore any module which is isomorphic to R mod I will be cyclic. So conversely, let M is isomorphic to R mod I for some ideal in I, for some ideal I in R. Now since this R mod I, R being a commutator ring with unity, so R mod I is generated by one bar. Here one bar, by one bar we mean the coset 1 plus I. Now every element of R mod I is actually a multiple of 1 plus I. Since R mod I is this, we note that M is cyclic, since this R mod I is cyclic, generated by one bar. Now let us recall what do we mean by annihilator of a module. So let us define this. So we have this definition. Let us consider an R module M. So let M be our R module. Let M be an R module. And then annihilator of M, which is then annihilator of M annihilator of M. Let us denote this by denoted by an of M is defined as, so this annihilator of M is actually a subset of R. So it contains all those elements in R which annihilate M, i.e. when M is 0. This is same as all those elements in R such that M is 0 for all M in M. So this annihilator of M, this is actually a subset. This is actually a subset of R. So this set consists of all those elements in R which annihilate, which kills this module M. Now it is a trivial exercise to prove that this annihilator of M is actually an idle of R. So let us make this as a proposition. So annihilator of M where M is an R module is an ideal of R. Now this is a trivial exercise to prove this is an ideal in R. What we have to prove? We have to prove this is closed under addition and scalar multiplication. So let us prove this in favored lines. So one can note here that this annihilator of M is non-empty, because this 0 in R that always annihilates M, because 0 dot M is always 0. Since 0 belongs to annihilator of M, we conclude that this annihilator of M is actually non-empty. Now let us take two elements in this set. What we have to prove? We have to prove their sum is also in this set. Now to prove A plus B is in this set, we have to prove A plus B annihilates M. So now A plus B of M, this is same as using the module actions. This is actually AM plus BM, which is actually 0. Now this is true for, now this M is an element of module M. Now why this is 0? Because A is an annihilator, so it annihilates the module M, so therefore AM will be 0. Similarly BM will be 0. So this is true for all M in M. This implies this module, this A plus B is an element of annihilator of M, because it annihilates the module. Now to prove annihilator of M is closed under scalar multiplication, let us choose an arbitrary element R in R and some element A in this annihilator of M. Now what we have to prove? We have to prove R times A is actually an element in annihilator of M. So these two elements are arbitrary. Let R and A be arbitrary. So they are chosen arbitrarily. Now R of A M. So once again we must observe here that this is the multiplication operation in the ring here, and this is a scalar multiplication. Now since these two multiplications are compatible, so we get, and this is same as R of A of M. Now A being an element of this set, so it annihilates M, so it kills this little M. So this is R of 0, which is same as 0. This means that this annihilator of M is actually closed under this scalar multiplication. This implies R of A belongs to annihilator of M. Hence this annihilator of M is an ideal in R. Now we may have, now it is guaranteed that this set is non-empty because 0 always belongs there. Now those modules for which this annihilator M is trivial, they are called faithful modules, i.e. An R module M is called faithful if it is annihilator is actually a zero ideal. So this is the definition of faithful modules. So an R module M is called faithful if its annihilator is trivial. If annihilator of M is trivial. We have another definition, i.e. the definition of finitely generated modules. So let us consider an R module M. So let M be an R module then we call M, then M is said to be finitely generated. If this M is actually sum of M1 plus so on plus Mn, where these Mi's are submodules, cyclic submodules of M, where Mi's, where Mi is a cyclic submodule of M for all I. That is, each Mi is actually generated by a single element xi, or this Mi is actually R times xi. So that is what we mean by these submodules to be cyclic. So if Mi is actually this R times xi, then this M is Rx1 plus so on plus R xn, and this is same as the module generated by x1 plus so on plus xn, and this is same as an R module generated by these elements x1 so on xn. So this set is called the generating set. So let us write this down here, where x1 so on xn is called the generating set of M. So a module M is actually finitely generated if it is generated by finitely many elements. So we have an analogous result as we did in free groups. So we have an analogous result for modules. So this is a proposition. So we call an an R module M is actually direct sum of its submodules if and only if M is actually generated, if M is actually sum of these modules, and if I choose any Mi and take its intersection with the rest of modules, so this is Mi minus 1 plus Mi plus 1 plus so on plus Mn. This has to be the null module, the trivial module. So this should be true for all I where this I varies between 1 and n. So in that case, M is said to be direct sum of these modules. So one should note here, we take intersection of this Mi with all other Mj's where J is not equal to I. Sum of Mj's where J is not equal to I. So alternatively, an R module M is said to be direct sum of these submodules M1 through Mn if each element of M is uniquely expressed as sum of elements of these Mi's. So alternatively, the R module M, the R module M is direct sum of M1 through Mn if and only if every M in M is uniquely expressed as so this M has this unique expression M1 plus so on plus M, and where this Mi, this is in this little Mi is in this big Mi for all 1 less or equal to I less or equal to n. So this is the alternative definition of an R module to be the direct sum of these submodules. Now finally we have one more definition, that is the definition of free modules. So let us write this down here. So when do we call an R module M to be a free module? So let us consider a cyclic module M. So a cyclic R module M. So if M is cyclic, so M is of the form R times X, is said to be free, is said to be free if annihilator of this x, this is actually 0. So this is the definition of a free module. Now if M can be expressed as direct sum of these M alphas, where each M alpha is a cyclic free R module. So an R module M is said to be free if M can be expressed as direct sum of M can be expressed as direct sum, so M is actually direct sum of these M alphas, where this direct sum runs over alpha. So where each M alpha is cyclic free module, is cyclic free module. So in that case we say this R module is free. So let us do some homework here and let us understand these free modules. So if M is our cyclic module, so that means M is given to be an R module, and it is given that this M is cyclic, so it is generated by this X, i.e. M is R times X, which is same as X, model generated by X. So in that case we have a homomorphism phi from this R to M, where an element A is mapped to AX. Now one can see this is a surjective homomorphism. Now if annihilator of this X is 0, then the kernel of this homomorphism is just the trivial ideal, i.e. that is a 0. So in that case, as we have seen earlier, R mod kernel of phi is isomorphic to M. Now kernel of P here, it is actually the annihilator of M, because if we look at this kernel of phi, it contains all those elements of R such that phi of A goes to the identity here, that is 0. That is all those elements in R such that phi of A, which is AX, is equal to 0 for all X in M. Now this is like this, so this X is in M. So if one can note here, this is actually the definition of the annihilator. So this is annihilator of this element X here, but annihilator of X is same as annihilator of M, as M is generated by X. Now if annihilator of this x is 0, if annihilator of m is 0, then in that case R is isomorphic to M. So for a cyclic R module M where the annihilator of its generator is just 0, then they are isomorphic. Now if, as seen above, we had defined an R module M to be free module if M is direct sum of free cyclic R modules. So suppose M is suppose direct sum of M1 plus so on plus Mn, where this M1 is free cyclic R module, this Mn is also free cyclic R module. So in that case each Mi will be isomorphic to R. So the another definition for M to be free is that it is isomorphic to some copies of the underlying ring. So in this case we have n submodules. So an R module M is sometimes, and this is an alternative definition for a free R module, that is an R module M is free if M is isomorphic to some copies of underlying rings. Here in this case the underlying ring is R. So if M is isomorphic to some copies of R here, then M is said to be free. Now this follows from this definition here.